Welcome to this problem walkthrough. Today, we'll explore an interesting tree-based problem from LeetCode, problem number 687, longest Univalue path. This problem challenges us to traverse a binary tree and find the longest path where all nodes share the same value. Let's dive in and break it down step by step. In this problem, we are working with a binary tree where each node contains an integer value. A key concept here is the idea of a univalue path, which is a path in the tree where every node along the path has the same value. Importantly, this path does not need to pass through the root of the tree. Now, the length of such a path is defined by the number of edges connecting the nodes in the path, not the number of nodes themselves. Our task is to determine the length of the longest univalue path in the given tree. The input to this problem is the root of the binary tree, represented as a tree node object. Each tree node has three attributes: val, which is the integer value of the node, and left and right, which refer to its left and right child nodes, respectively. The output we need to return is a single integer representing the length of the longest univalue path in the tree. Let's look at an example to clarify the problem further. Here we have a binary tree where the root node has a value of 5. Its left child has a value of 4, and its right child also has a value of 5. Moving further down, the left subtree has two child nodes, both with the value 1, while the right subtree has a single child node with the value 5. The output for this example is 2, as the longest univalue path is along the right subtree, following the nodes with the value 5. This path consists of two edges, giving it a length of 2. Now consider another example. In this tree, the root node has the value 1, the left child has the value 4, and the right child has the value 5. The left subtree has two child nodes, both with the value 4, and the right subtree has a single child node with the value 5. Here, the output is also 2, because the longest univalue path is in the left subtree, formed by the nodes with the value 4. This path spans two edges. In a slightly more complex example, we add another node with the value 4 as a right child to one of the existing nodes in the left subtree. This creates a longer univalue path of length 3, as the path now includes 4 nodes with the value 4 connected by 3 edges. To wrap up, there are some edge cases we need to consider. If the tree has only one node, then there are no edges, so the longest univalue path is 0. Similarly, if all the nodes in the tree have distinct values, there are no valid univalue paths, and the output is also 0. On the other hand, if all nodes in the tree share the same value, the longest univalue path spans the entire tree. Lastly, for unbalanced trees, like skewed trees, the algorithm must handle deep recursion efficiently to avoid stack overflow errors. Remember, the path does not need to pass through the root, and it is defined by edges, not nodes. This means a single node cannot form a path by itself. To solve the longest univalue path problem, we first consider a brute force approach. The intuition here is straightforward. For each node in the tree, we calculate the longest path where all nodes share the same value as the current node. This involves traversing the subtree of every node, checking if the values along each path are uniform, and then determining the maximum length from these paths. The process involves recursively calculating the univalue path length for the left and right subtrees at each node, ensuring that these paths only include nodes with matching values. While this approach is simple to understand, it has a major drawback. In the worst case, such as a skewed tree, we would end up traversing the tree repeatedly for each node, resulting in a time complexity of n squared. This makes the brute force approach computationally expensive and inefficient for larger trees due to redundant calculations. Now, to address the inefficiency of the brute force approach, we turn to an optimized solution using post-order traversal. The key observation here is that the longest univalue path in a binary tree can be determined by taking the maximum of 3 components: the longest univalue path in the left subtree, the longest univalue path in the right subtree, and a path that passes through the current node, provided its children have the same value as the node. Using post-order traversal, we calculate the result for the subtrees first and then use these results for the parent node, ensuring we eliminate redundant computations. During this traversal, we perform a depth-first search, calculating the univalue path length for the left and right children of each node. If a child matches the current node's value, we extend the path, otherwise, we reset it to 0. At each step, the global maximum path length is updated. This approach is highly efficient, with a time complexity of O(n), since each node is visited only once, and a space complexity of O(h), where h is the height of the tree, due to the recursion stack. The optimized post-order traversal provides significant advantages. It avoids redundant calculations, making it highly efficient and ideal for handling large trees. Additionally, we could consider an alternative approach using dynamic programming. In this idea, we use memoization or a hash table to store the Univalue path results for each node. This would allow us to avoid recomputing the path lengths when the values are needed for the parent nodes. The process involves a top-down traversal starting from the root, storing results for each node. While this approach also achieves a time complexity of O(n) and a space complexity of O(h), its implementation is more complex compared to the post-order traversal approach. Thus, while dynamic programming is a viable alternative, its added complexity makes it less appealing in practice. Ultimately, the optimized post-order traversal approach is the chosen strategy for this problem. It is both time efficient, with a complexity of O(n), and space efficient, with a complexity of O(h), making it well suited for large input trees. Moreover, its simplicity in implementation further strengthens its appeal, as it avoids the need for additional data structures required in the dynamic programming approach. While the brute force method is conceptually simpler, its inefficiency on larger inputs renders it impractical. The key insight in the post-order traversal solution is the realization that the Univalue path length at each node can be computed bottom-up by leveraging results from its subtrees. This eliminates redundant calculations and significantly reduces complexity. Therefore, this approach strikes the perfect balance between efficiency and simplicity, making it the most practical choice for solving this problem. This problem asks us to find the longest Univalue path in a binary tree, where a Univalue path is defined as a sequence of connected nodes that all share the same value. The length of this path is measured by the number of edges between the nodes. To solve this, we first need to understand the structure of the binary tree. Each node in the tree has a value and may have up to two children, one on the left and one on the right. The key challenge is to determine the paths where all nodes have the same value and then calculate their lengths. These paths may extend through one child, both children, or neither, depending on whether the child nodes share the same value as the parent. To efficiently traverse the tree and calculate these values, we use a recursive depth-first search, specifically a post-order traversal. This ensures that we process the children of a node before using their results to compute the path for the parent. A helper function, DFS, node, will be defined to calculate the longest Univalue path originating from the current node, allowing us to build the solution recursively. To implement the recursive solution, the first step is to handle the base case. If the current node is null, we return 0, as no path can exist. Next, we make recursive calls to compute the longest Univalue paths for the left and right children of the current node. These are stored in left_length and right_length, respectively. Then, we check whether the left and right children contribute to a Univalue path. If the left child exists and its value matches the current node's value, we extend the left Univalue path by 1, otherwise, we set it to 0. The same logic applies to the right child. After computing the Univalue paths for both sides, we update a global variable, max_length, which keeps track of the longest Univalue path seen so far. This value is updated by considering the combined length of the left and right Univalue paths passing through the current node. To ensure the recursion remains valid, we return the maximum of the left and right Univalue paths. This value represents the longest single-arm path extending from the current node, which will be used by its parent during further calculations. Once the recursive function is implemented, we initiate the traversal by calling DFS, root, on the root of the tree. This starts the depth-first search and ensures that the entire tree is processed. The final result is stored in the global variable max_length, which is returned as the solution to the problem. There are a few key insights to highlight here. First, the post-order traversal is critical because it guarantees that we compute the Univalue path lengths for the children before using them for the parent. Second, the use of a global variable max_length helps us track the longest path without recomputing values for parent nodes repeatedly. Lastly, we account for edge cases such as a tree with only one node, where the path length is 0, or a tree where no two nodes share the same value, also resulting in a path length of 0. In contrast, a fully balanced tree where all nodes have the same value would yield a path length equal to the height of the tree minus 1. These considerations ensure the solution is robust and handles various scenarios effectively. The binary tree serves as the primary input structure for this problem. Each node in the tree contains a value and pointers to its left and right children. As we traverse the tree using the recursive function, we use a global variable, max_length, to track the longest Univalue path encountered so far. This approach avoids redundant calculations and ensures that the maximum path length is updated efficiently during each recursive step. In terms of complexity, the time complexity of the solution is O(n), where n represents the number of nodes in the tree, because each node is visited exactly once during the depth-first search. The space complexity is O(h), where h is the height of the tree, as the recursive call stack will have at most h levels. To further optimize the solution, we minimize redundant computations by using a single traversal and updating the global maximum only when necessary. Additionally, early exits for nodes that do not contribute to a Univalue path help reduce unnecessary recursion, making the algorithm more efficient. The pseudocode for the solution consolidates all these steps. We define a recursive function, DFS as node, which handles the base case by returning 0 if the node is null. It then recursively computes the Univalue path lengths for the left and right children. Depending on whether the children's values match the current node's value, we extend the left and right Univalue paths. The global variable max_length is updated with the sum of these paths to track the longest overall path. Finally, the function returns the maximum of the left and right Univalue paths, representing the longest single path extending from the current node. After defining this function, we initialize self.max_length to 0 and call DFS, root, to start the traversal. The value of self.max_length at the end of this process gives the length of the longest Univalue path in the tree, which is returned as the result. This complete implementation ensures that all aspects of the problem are addressed efficiently and accurately. The problem requires calculating the longest Univalue path in a binary tree, where all nodes in the path share the same value. The solution uses depth-first search, DFS, to traverse the tree and calculate the longest path recursively. 1. Global variable self.max_length. This variable tracks the maximum Univalue path length encountered during the traversal. It is updated whenever a longer path is found. 2. Recursive function DFS, node. This function performs a post-order traversal of the tree. For each node, it recursively computes the longest Univalue paths in its left and right subtrees, left_length and right_length. It checks whether the child nodes share the same value as the current node. If so, it extends the path length, left_path and right_path. 3. Update self.max_length. The combined path length through the current node, left_path plus right_path, is compared to the global maximum, and the maximum is updated if necessary. 4. Return value of DFS. The function returns the longest single path from the current node, which is the maximum of left_path and right_path. This ensures the recursion propagates the correct path length to the parent node. 5. Edge cases. If the root is null, the function handles it gracefully by returning 0. The algorithm also accounts for nodes with no children or nodes with mismatched values. The DFS traversal ensures each node is visited once, making the time complexity O(n), where n is the number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we begin the Java implementation of the solution. First, we import the necessary utilities and define the solution class. Inside this class, we declare a private variable maxLength to keep track of the longest Univalue path length that we find. The main method, longest Univalue path, takes the root of the binary tree as input, initializes maxLength to 0, and then calls a helper method named DFS, which performs a depth-first search traversal of the tree. The result of this traversal is returned as the maximum Univalue path length. Now, the DFS method itself is defined to handle the recursive traversal. If the current node is null, it simply returns 0, as there is no path to compute. Otherwise, it calculates the path lengths for the left and right subtrees by recursively calling DFS on the left and right child nodes. These lengths are stored in left length and right length. To account for paths that can extend through the current node, we introduce two variables, left path and right path, both initialized to 0. Here, we check if the value of the left child matches the value of the current node. If it does, we update left path to be 1 plus the length of the left subtree path. This inclusion ensures that we are building a Univalue path extending through the left child when the values align. Next, we perform a similar check for the right child. If the value of the right child matches the current node's value, we update right path to include the Univalue path extending through the right child, incrementing it by 1 plus the right subtree's path length. Once we have the left path and right path, we update the max length variable by comparing it with the sum of these two paths. This step ensures that we are always keeping track of the longest Univalue path found so far, even if it spans multiple nodes through both the left and right subtrees. Finally, the method returns the maximum of left path and right path to the caller. This return value represents the longest Univalue path that can extend from the current node upwards. At the bottom, we also define the treeNode class, which represents each node in the binary tree. It includes fields for the node value, as well as references to the left and right children. This encapsulated structure allows us to work with the binary tree nodes seamlessly throughout the implementation. Here we start with the simplest possible scenario, a single node tree. The tree consists of only one node with the value 1. Since there are no edges in this tree, there is no path to consider, and the length of the longest Univalue path is 0. When we execute the algorithm, we first call the DFS function on the root node. Because this node doesn't have any left or right children, the recursive calls to DFS return 0. The variables left_path and right_path also remain at 0 because there are no child nodes to contribute to the path. Finally, we update the global self.max_length by adding left_path and right_path, which results in 0. The function then returns 0, the maximum of the two path lengths. The result for this example is that the longest Univalue path has a length of 0. Now let's consider a linear tree where all nodes have the same value of 1. This tree has 3 nodes connected in a single line, and the longest Univalue path spans the two edges connecting the nodes, yielding a length of 2. To compute this, the DFS function is first called on the root node. From there, the recursion proceeds down the right child nodes. At the last node in the chain, both its left and right children are none, so the recursive calls return 0. Backtracking to the second node, we calculate left_length and right_length, both of which are 0 because there are no left children and the right child returns 0. This sets the stage for the next calculations. At the second node, we determine that right_path is equal to right_length plus 1, which is 1, because the value of the right child matches the current node's value. We then update self.max_length to 1, as this is the longest path encountered so far. The function returns 1 to the previous level. Back at the root node, we again calculate left_length and right_length. Here, left_length remains 0 because there is no left child, but right_length is 1, as returned from the second node. This allows us to calculate right_path as right_length plus 1, which equals 2. With this, we update self.max_length to 2, reflecting the longest Univalue path in the tree. The function then returns 2. Overall, the result is a longest Univalue path of length 2. In this balanced tree with mixed values, the longest Univalue path is found in the right subtree, following the nodes with value 5. The path length is 2, corresponding to the two edges connecting the 3 nodes with the same value. To calculate this, we first call DFS on the root node, then recursively descend into the left subtree. At the left child node, which has the value 4, we further call DFS on its left and right children, both of which are leaf nodes with value 1. Since these leaf nodes have no children, the recursive calls return 0. Back at the node with value 4, we calculate left_length and right_length as 0, and since its children do not share its value, self.max_length remains unchanged at 0. The function then returns 0 for this node. Next, we explore the right subtree of the root, starting with the right child node, which has the value 5. We proceed deeper into its right child, another node with value 5. At this deepest node in the right subtree, both its left and right children are none, so the recursive calls return 0. Backtracking to its parent, we calculate left underscore length and right underscore length as 0, but since this node's value matches its child's, we compute right underscore path as right underscore length plus 1, which is 1. This updates self.max underscore length to 1. The function then returns 1 to the previous level. At the root node, we calculate left underscore length as 0 and right underscore length as 1, the value returned from the right subtree. Since the right child's value matches the root's value, we calculate right underscore path as right underscore length plus 1, yielding 2. This updates self.max underscore length to 2, the longest Univalue path found in this tree. The final result is a longest Univalue path of length 2. The time complexity of our solution is O(n), where n represents the number of nodes in the binary tree. This efficiency comes from the way the DFS function is designed. It visits each node exactly once, performing a constant amount of work at each step. For every node, the algorithm calculates the longest Univalue path by recursively determining the lengths for the left and right subtrees, comparing the node's value with its children, and updating the global maximum path length. All of these operations take O(1) time per node. Whether we consider the best, average, or worst-case scenarios, the time complexity remains O(n). Even in a scenario where all node values differ or all are the same, every node is still traversed exactly once. This uniform behavior makes the time complexity consistent at O(n), regardless of the tree structure. The space complexity of the solution is O(h), where h is the height of the binary tree. This is primarily determined by the recursion stack used during the depth-first search traversal. In the worst-case scenario, such as a completely skewed tree, the recursion stack could reach a depth equal to the total number of nodes, making the space complexity O(n). However, in the best-case scenario of a perfectly balanced binary tree, the height of the tree is O log n, leading to a space complexity of O log n. Importantly, the algorithm does not allocate extra space beyond the recursion stack, as all computations are performed in constant space at each step. Therefore, the overall space complexity is O(h), where h reflects the tree's height, which can vary between log n and n depending on the tree's structure. A naive approach to solving this problem might involve calculating the Univalue path for each node individually, traversing the tree multiple times. For every single node, you would compute the Univalue path by traversing its entire subtree. This repetitive process leads to a time complexity of O(n) squared in the worst case, as there are n nodes, and each subtree traversal could take O(n) time. The optimized approach, which is the solution we've been discussing, avoids this inefficiency by performing a single depth-first search traversal. During this single traversal, the longest Univalue path for each node is calculated and propagated upward, reducing the time complexity to O(n). In terms of space complexity, both the naive and optimized approaches use O(h) space for recursion, but the optimized approach achieves a significant improvement in runtime by eliminating redundant computations. Now, let's provide a mathematical perspective to reinforce the big O analysis. With a depth-first search traversal, each node is visited exactly once, and since the work done at each node is constant, the time complexity is O(n). Regarding space complexity, the depth of the recursion stack directly depends on the tree's height, h. For balanced trees, the height is O log n, leading to O log n space complexity. For skewed trees, where the height is equal to the total number of nodes, the space complexity becomes O(n). By avoiding redundant computations, the solution improves significantly over naive methods, proving its efficiency in both time and space. This balance between O(n) time complexity and O(h) space complexity demonstrates the effectiveness of the current approach. When working on problems like the longest Univalue path, there are a few common mistakes to avoid. One frequent issue is not handling edge cases, such as when the tree is empty or consists of only one node. These scenarios can lead to null pointer exceptions or inaccurate results if not handled properly. The solution is to explicitly account for these cases in your base conditions, whether you're using recursion or iterative methods. Another common pitfall is inefficient recursive calls, where the same subtree calculations are repeated multiple times, leading to unnecessary time complexity. To address this, you can incorporate memoization or pass intermediate results to avoid redundancy. Additionally, many people fail to distinguish between local results at each node and the global result required for the entire tree. To ensure accuracy, use a helper function to update a global variable consistently during traversal. Finally, it's important to avoid confusing the parent-child relationship in the tree. For Univalue paths, you need to ensure that the directionality of your comparisons aligns correctly with the intended traversal logic. Clearly defining how values are propagated during recursion can help maintain this consistency. Another common mistake is misdefining the base case in recursive solutions. Overcomplicating or oversimplifying this can lead to infinite recursion or incorrect outputs. To avoid this, consider the simplest scenarios, such as a single node or a null tree, and make sure the base case handles them properly. As for interview preparation, it's essential to recognize that problems like these often involve depth-first search or post-order traversal. Understanding how results propagate up the tree is a fundamental skill. Additionally, you should be comfortable managing global state, as many tree-related problems require tracking values like the maximum diameter or path length. While brute force approaches can help you understand the problem initially, interviewers expect you to transition to optimized solutions quickly, such as using dynamic programming or memoization techniques. Lastly, be prepared to discuss edge cases like highly unbalanced trees, trees where all nodes have the same value, or null trees during interviews, as these are commonly tested scenarios. If you're preparing to solve the longest Univalue path problem, it's helpful to study related problems that share similar concepts. For instance, problem 543, diameter of binary tree, focuses on finding the longest path between two nodes and involves similar traversal techniques. Problem 124, binary tree maximum path sum, is another example that requires careful management of both local and global states while solving. Of course, the longest Univalue path problem itself is directly relevant and worth revisiting to strengthen your understanding. Additionally, problem 104, maximum depth of binary tree, serves as a simpler warm-up exercise that helps you practice tree traversal before tackling more complex challenges. Exploring these problems will give you a broader perspective on handling different aspects of tree-based questions. There are several alternative approaches you can use to solve tree problems like the longest Univalue path. A common method is depth-first search with recursion, which is intuitive and straightforward to implement. However, this approach can run into stack overflow issues with very deep trees unless handled carefully. Another option is iterative DFS using an explicit stack, which avoids recursion but requires meticulous stack management, making it more error-prone. Dynamic programming on trees is another powerful approach, especially for problems where reusing sub-problem results is advantageous. While efficient, it can be more challenging to implement due to the need to manage multiple states simultaneously. Lastly, breadth-first search can also be used, though it's generally less suitable for recursive path-based problems. Each approach has its trade-offs, so it's important to choose the one that best fits the problem constraints and your implementation comfort level. Great job making it to the end. In this session, we tackled the longest Univalue path problem and reviewed efficient strategies like DFS to solve it. We covered key takeaways, including optimizing for time and space complexity in tree problems. Remember to practice similar problems to solidify your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!